And I have the great honor of introducing Stefan Karpinski, and no introductions necessary. Take it away.
All right, thank you. All right, so this talk is about the collision-resistant splittable RNG that we use since 1.11, I believe, for structured parallelism. And that's a bit of a word salad, but I'll be explaining a lot of this as we go. I have tentatively named it Bifold because it needed a name. So a little bit of RNG algorithm history. This is before what we're really talking about in this talk, but we used to use Mersenne twistor from the beginning of time. DSFMT specifically, which is like a slight variation. It's huge. It's a very big random number generator, and it's not especially good. So it's not good by modern standards. In 1.7, we switched to Zoshiro 256++, which is a good modern generator. It's also small. It's 32 bytes. And this enabled a very cool thing, which is that instead of having a single global shared RNG that you have to lock to use, and locking is bad, but also if you have multiple threads using it, who knows who got what value in what order? It sort of becomes unpredictable. So in 1.7, with the changing to Zoshiro, each task gets its own local RNG that lives in the task object. And since it's only 32 bytes, that's reasonable to do. And this gives us reproducible RNG sequences even when we're doing tasks and multi-threading. And it only depends on the seed and then the shape of the task tree, which is predictable. It works great, and this is what I'm showing is in 1.7 through 1.9, except for this. So all I did there is I inserted an async nothing in there, and it changes the second RNG value. First one's the same, second one it's like, oh, what? Okay, why does this happen? All right, so the reason this happens is when you fork a task, the child's RNG needs to be seeded as well. You can't just copy the parent RNG because then they'd both go off and produce the exact same values, and that's not what you want. So the child was seeded by sampling from the parent RNG, and of course that modifies the parent RNG's state. And I don't show it here, but you sample the RNG 4 times. So you can get the same value if you can go back here and instead of doing async nothing, you replace it with just sampling the RNG 4 times, then you do get the same values. But still, this is undesirable. Surely someone has worked on this. So we go to the literature and we see, yes, in fact, there are some very interesting papers on exactly this. A paper called it's not called DotMix, but the algorithm is called DotMix. It's got this longer title. Leiserson et al. Out of MIT for the Cilk parallel runtime. And this has been a huge inspiration in general for Julia and the way its tasks work. So it's not too surprising that they have thought about this. So like, okay, great. These are very smart folks. They've thought about this. Hopefully they have a good solution. And then Guy Steele of Java fame also has a paper about introducing a thing called SplitMix, which is derived from DotMix. All right, I'm going to explain a bit how these work. I'm going to have to fly through these slides because there's a lot. So DotMix has this cool concept, the pedigree vector of a task. And it's recursively defined. The root task has an empty pedigree vector. And if a parent has a pedigree vector with these coordinates, k1 through kd-1, its children are at depth d in the task tree. So the root is up at the top, and you're down at level d. So these are all of that task's children. The kdth child has pedigree vector that's just, you stick the index kd at the end of the pedigree vector. And so it's not too hard to see that every task gets a unique pedigree. Of course, the problem is this takes an arbitrary amount of data. We don't have that in tasks, so we need to compress this down to something of fixed size somehow. The core idea for DotMix is that you take this vector and you take a dot product of it with random weights. The same random weights for every time you do this, but randomly generated weights. And you can prove that the chance of collisions between those dot products between distinct tasks is only 1 out of 2 to the 64 if you're using a 64-bit dot product. And then you apply a bijective nonlinear finalizer based on murmur hash to like scramble the bits and make it nonlinear. And then that finalized value is used to seed your main RNG that you use for actually generating values that you want to use. Very cool idea, very cool paper. They do a lot of this stuff very explicitly, and it's kind of heavyweight, and they actually generate a vector that they keep in memory, and it's shared of like randomly generated weights, 1,024 of them. So it's not super optimized, but it's like pretty clever. The details of the proof, we're gonna look at this a little bit because it turns out to be important later. So this, this is the definition. I write chi for the dot product. I don't know, I just made it up. It seemed like a good letter. It's the sum of the weights times the coordinates. And then it's done modulo p, where p is a prime. This is crucial. It's necessary for the proof of collision resistance. And it is annoying because it complicates the implementation quite a bit, because you can't just use native arithmetic. You have to simulate this modulo p arithmetic. And they use the largest prime that fits in 64 bits, which is this. Okay, so here's the proof, very quickly. Suppose you have 2 different tasks and they have the same chi value. So these 2 dot products are equal for 2 different tasks. So they're different, so they have some coordinate that's different. So we can let j be the coordinate of one of the coordinates where they differ. So this difference here, kj minus kj prime, is non-zero. And we have the weight times this non-zero thing is equal to some difference, delta. We don't actually care what delta is. It's the difference of all the rest of the terms, but it is arbitrary. We don't actually care what it is. But the key thing here is that because it's a prime modulus, you can invert that difference, and you get wj is equal to the inverse of that difference times delta. And there's only one wj value that satisfies this. And that means that the probability of this happening is very unlikely. There's only a 1 in p, and p is almost 2 to the 64. Cool proof, very nice. All right, so SplitMix is the next paper. Funny story, I read this paper and the authors spent a lot of time on an optimized version of DotMix, and I thought that was SplitMix. It is not. But in my defense, they spend 12 out of 20 pages working on this optimized version of DotMix, and then they basically take a left turn and they're like, you know what? Forget that, we're gonna do something completely different. Doesn't involve dot products. Like, it's a cool idea, but it's not. They claim that it's derived from DotMix, but I don't think so. It has like none of the same properties as DotMix, but it is a cool idea. So what SplitMix actually is this. It's a very, very simple core random number generator transition. It's just the state plus gamma, where gamma is some odd constant. And then you do this, it's like a murmur hash type of finalizer, and that's the output. So the basic idea is it's an RNG where the state update is very simple, and you put all of the complexity into the output function. It's a little bit of a suspicious construct, but it passes tests pretty well, so like, okay, it seems to be okay. So each task has 2 words of state. It has the main S, which is the main RNG state, and then gamma, which doesn't change in each task, but is different across tasks. And the cool idea they have here is that the flow is different than I expected. It's a clever idea. It's that as long as you can have a collision of the S part of 2 tasks, as long as the gammas are different, you still don't have a problem. So you basically get better collision resistance. And one of the cool things is this thing is designed so that you can generate random numbers from it and also fork it, which DotMix is designed to be an auxiliary RNG, not the main RNG, where SplitMix can do both. So that's cool. Now, do we want a thing that's an auxiliary RNG, or do we want something like SplitMix? So DotMix is explicitly meant to be just to seed your main RNG, whereas SplitMix can do both. But the problem is that if you use SplitMix that way, because of the way it works, it samples from itself to fork its children, and that's exactly what we're trying to avoid happening. So the way they use it, they seem okay with that. We don't want that, so we can't really use SplitMix the way it's intended. Here's my proof that we need an auxiliary RNG. Okay, our requirement is forking children must not change the main RNG state. But something has to change, because otherwise every child would be identical. So that something is the auxiliary state that we have to add QED. Like we have to add something. There has to be at least a 64-bit word that we add. What if we used SplitMix as an auxiliary RNG and then just used it to seed a main RNG? That's an option. It's not great because then we've got these two words, not just one, because it's got the S part and the gamma part, and it's 128 bits, and that's more than we want to add. And also, we should use all of the auxiliary bits for splitting, not generation, because we're not going to use it for generation, so that's wasted space. Like, we don't need that. Okay, so DotMix does this, and it has a cool collision proof, so let's try using DotMix. That was my thought. Okay, so in the SplitMix paper, they spend all this time optimizing DotMix. Basically what they do is they note that you can incrementally compute the dot product instead of recomputing the whole thing constantly. And what they end up doing is like, so each task has the cached dot product in it, and then when you fork, this is what you do. You increment the cached dot product by the weight for your current task depth, and then your child dot product is a copy of that cached dot product. They also improved a couple other things. They noticed that you can actually get away with a cheaper finalizer, and then they used a different prime modulus, which, who cares? Okay, so I looked at the DotMix stuff and the optimized version, and I was like, can we do this? Can we be even better? Partly this was laziness. I was like, I don't want to implement this prime arithmetic stuff. It's very annoying. And so much effort is put into both of these papers in trying to make it fast, and it's not helped by the fact that the JVM doesn't have unsigned integers. That makes everything more annoying. It would be really nice if we could just use native arithmetic. So back to the drawing board. Why do we need a prime modulus? Okay, it's for the proof of collision resistance, so that the difference between these coordinates is guaranteed to have a multiplicative inverse. But why are the pedigree coordinates arbitrary integers in the first place? Because the task tree is n-ary, because you can spawn, many children at each level. But this feels a little weird to me. Like, forking tasks is inherently binary. One task becomes two tasks. Like, can't we do this binary somehow? So I thought about that for a while, and I came up with a scheme where you assign IDs to your tasks instead of pedigrees, and then you can get a pedigree back out of it. But basically, the root node has ID 0. This is immutable. The ID of a node doesn't change, but you maintain a fork index. And this is not quite the task tree depth. It's not the same thing. But it's sort of, it's the thing that distinguishes the first child from the second child from the third child. But it keeps going. You keep it going through the children. Okay, so now here's the idea. The child ID is the parent ID plus 2 to the power of the parent index. So if you start with 0, the root node 0, its first child, you add 2 to the 1, or 2 to the 0, which is 1. So its first child has index 1. Its second child has index 2. Its third child has index 4. Its fourth child has index 8. The root node's children are all powers of 2. But then the first child's children are all going to be powers of 2 plus 1. So basically, you're being like very frivolous with the space of integers, but this is an arbitrary precision, so you have infinitely many integers. This is a way to give everybody a unique ID. And then you can turn the ID back into a pedigree vector because it's a bit vector. It's already a binary vector. Totally different tree shape, but this is a way to do it. Okay, so now we go back to the proof. The difference between coordinates is now either plus or minus 1. That always has an inverse. We don't need a prime modulus, we're done. Plus, there's no multiplication, so it simplifies the dot product. Now the dot product, you have the weights, but the difference between the coordinate is always either 1 or 0. Those are the only things. So either do or don't add a weight at a particular level. So this becomes the incremental dot product computation. It's super simple. Child dot product is parent dot product plus the weight at the fork index. That's it. Okay, random weights. DotMix does this thing where they pre-generate an array of actually random weights. It's shared between all tasks, so it's not terrible. It's 8 kilobytes, but like, I don't know, it's just sort of 8 kilobytes of random data hanging around. And if the task tree gets deeper than 1024, they just recycle weights, which seems nuts. Can't we do something else, like use a PRNG to generate weights? Okay, so that's what I'm gonna do. I'm gonna use a PRNG. Okay, so this is the idea. Use a PRNG to generate random weights. The state size is 64 bits. The output size is also 64 bits. You can't have duplicates, but that's bad for a general RNG, but it's fine, and it's actually good in this case because you don't want duplicate weights. Arguably the best PRNG for this is this PCG 64 one. So that's what we'll use. And the basic design of that, it's a linear congruential generator core, and then a pretty strong nonlinear bijective output function. Okay, so this is what Julia 1.10 does. I'll call it .mix++. Generate weights with PCG. It adds one word of state to the task. And you accumulate a dot product into the main RNG state. That's like a clever change that I decided to do. I was like, instead of accumulating this dot product in the task state somewhere else, we've got these random bits. Why don't we just accumulate into there? And this is this is translated into Julia. It's implemented in C, but this is roughly the code for it. So you can see you get your weight from the previous auxiliary RNG state. You update the auxiliary RNG. You use the previous value state as the weight because it's better instruction level parallelism. It's a classic trick. Then this bit is the PCG output function, and then you just update the main RNG state with that weight. And so you're basically accumulating the dot product into the main RNG state. All right, so there's a little bit of a complication. Our main RNG actually has 4 64-bit registers, not 1, because it's a 256-bit RNG. So what we do is we actually do 4 variations on that with different constants, and we accumulate 4 different independent dot products. And that has the benefit of making our collision resistance 1 over 2 to the, 1 and 2 to the 256, which is great. Like, that's incredible collision resistance. Win-win design, right? We avoid extra task state for the dot product accumulation, and we massively increase our collision resistance. Great. This is roughly what it looks like. So you get the weight, and you advance the auxiliary RNG, and then for each register of the Zoshiro 256, you do the thing that was on the previous slide. But you're indexing into an array of constants that are different in each one. And the weight, you perturb the weight by some random constant so that they don't all start out the same. They're kind of in different parts of the space before you apply the PCG finalizer. Okay, so this might be suspect, this business of accumulating into the main RNG. Is it okay? So the DotMix paper actually suggests seeding the dot product with random initial values. So that is okay. We're effectively seeding with whatever happened to be in the main RNG. You can actually make the collision resistance proof work even when people are using the main RNG in between these things. And it mainly comes down to the fact that we don't care what that delta number is in the proof. It doesn't matter. So if it's got random crap added to it, the proof still works. You also need to know that the RNG advance of the main RNG is bijective. All right. Is this all good? It seems nice. It's a nice design. But unfortunately, in February 2024, FUBAR IV2 who, regulars on Discourse will be familiar with. I don't know how he looked at this and was like, oh, it's got this problem, but he did. He noticed that there's an observable linear relationship between outputs of the RNG when you spawn 4 tasks in a certain way, which I will explain. This is the code that I made some code to do this because his explanation was a little inscrutable. Basically, you spawn some tasks and generate random values in them and then fetch them. And then this relationship down at the bottom holds between those random numbers. This only produces 9 different values. It basically means this is approximately 0, except there's like 9 different values of 0. Okay, so why? Here's the task diagram. Okay, so we start with task 0, 0. It spawns a child, and we add the weight 1, and that is added to the state of task 0, 1, 0. Then we spawn a second child and add weight 2, and that's task 0, 1. And then task 1, 0 spawns its own child and adds weight 2. Okay, so now we've got this relationship, and therefore the dot product of 0, 1 plus the dot product of 1, 0 is equal to the dot product of 0, 0 plus the dot product of 1, 1. Oops. So what that means is that if they started out with the same main RNG state, then they all end up in different states, so the collision doesn't happen, but if you add their states in this certain way, then that has a relationship that is observable. So that's not great. I mean, it's like, who would be doing this? I don't know, but like, we still don't want this to happen. So we didn't like patch it on 110. 110 still does this, but we got to fix it. This leads you to think, is the DotMix thing broken? Did they screw this up? The answer is no. So the core DotMix dot product computation does have this inherently. It's a linear dot product. It has this property. But these people are professionals, and they obviously knew this, and they applied a very strong output finalizer function to it. Me, being not a professional in this field at all, I was like, the weights are random. That seems good enough, right? And like, no, obviously not. This was dumb. I should have realized you need to have that finalizer, and I just didn't do it. So can we apply the finalizer and still do what we were doing? Unfortunately, no, because in order to apply the finalizer, you're accumulating the dot product in the main RNG. You want to apply the finalizer before perturbing the main RNG, but at that point you've already lost your dot product. You could like undo it and keep applying it, but that would be a lot of extra work. So we'd have to accumulate the dot product outside the main RNG, and now that increases every task size by the size of the accumulator. So we could add 1 extra word for accumulation to every task, 64 bits, but then we don't get our like nice 1 and 2 to the 256 collision property anymore, because we actually need 4 accumulators for that to work. That's a lot of stuff to add to every task. So this kind of sucks. Is this recoverable? Can we fix it somehow? So my thought was nonlinear dot products, of course. The dot product is inherently problematic for this. Could we do something that's nonlinear? What is the very bare minimum property that we need to make the collision proof work? And so, okay, let's generalize plus. So this is the plus, this is the version in 1.10. What if we replaced plus with any, so it turns out we can replace plus with any doubly bijective reducer function. Doesn't have to be commutative, doesn't have to be associative, doesn't have to be linear. And what you're accumulating then is no longer a dot product, it's a left fold by this beta reduction function over all the active weights of the task. We can generalize the proof. The proof still works. You have to tweak it a little bit, but basically the general idea, and this is a little hard to follow on so quickly, but suppose 2 different tasks of the same reduction value. We start at the same place. You can rewind through all the indices where the task IDs are the same until you hit one where they're different. And you can do that because it's mapping, its beta is bijective in its first coordinate. You can also rewind through matching, through corresponding uses of the main RNG between the two tasks, so that works. That's the other part of it. And then you end up in one of two situations. Basically, you have beta of the state and weight of the first task equals this other beta reduction, or it equals alpha of some state where alpha is the main RNG transition. And so either of those is basically this beta of a state times and a weight is some arbitrary constant. And there's only one value of W that happens for. So this is the essential part of the collision resistance proof. It still works. And it's a probability of 1 over 2 to the 64 for each register. So we get the whole 2 to the 256 collision resistance. So collisions are practically impossible. And the nice thing about this is now we don't have to worry about the, we don't have to worry, we can accumulate in the main register basically, because we have this nonlinear reduction function, so we don't have the linearity problem anymore. So this is it, this is bifold. This is what we do in 1.11 and greater. So it's very similar to before. You have this like LCG and you get the weight out, and then you get the state of the main RNG for the register. You XOR it with a random constant. You do this doubly bijective multiplication function. This could be anything really. This could be plus or times, but I like this one. And then you do the PCG finalizer with a per register multiplier, and then you save it back into the register. Some design notes, we use the LCG state directly as a weight rather than PCG 64. Good enough for this task. It's too weak for a general RNG, but we're just generating weights that we want them to be somewhat unpredictable. They don't have to be perfect. We XOR the common weight with a different constant per Zoshiro register, puts you in a different part of the space. It's helpful there that XOR doesn't commute with multiplication or addition, because those are things we do around it, so that is nice. This bimul function, it's a little like non-obvious that this is bijective in both arguments, but it is. And then we finalize with a per register variant of PCG. And then we accumulate into the main RNG. So that is, and again, that's unsafe for DotMix, but it's safe for Bifold because of the nonlinear accumulator. All right, so we wanted a task forking not to affect the main RNG. We need some auxiliary state, but we want to minimize it. So possible algorithms, if we use SplitMix, we need 128 bits of extra state. If we use DotMix, we also need 128 bits of extra state if we use it in a way that's not broken. With Bifold, we get away with only one extra word, and we get really good collision resistance. The fork operation is fast and simple. The dot product is actually not a dot product, and we can safely accumulate into the main RNG and interleave it with main RNG usage. We have a proof that that is fine, and the collision probability is like astronomically impossible. So there we go. That's it. Thank you.
Questions?
I know, it's a stunning amount of material preparing these slides. There was at one point where there were 58 slides in this deck, so I cut it down considerably.
Thank you. This was also a really fun community story. I'm curious, what background does someone need to obviously see the linear relationship? Like,
I don't know how you see it, obviously. We'd have to ask him. Obviously, I didn't see it. People have amazing minds. I do know he does a lot of crypto stuff, so maybe that helps. I'm not sure. There's another question in the back.
Kind of a weird question, but the LCG that was implemented for this, is that callable anywhere, or like can someone like import that or anything?
Oh, the LCG is like one line of code.
Okay.
It is literally multiply the state by a constant and add 1.
Okay, yeah, I was originally going to ask about the PCG, and then at the end, it's just like, oh, you.
Oh, and then the PCG is another 3 lines of like bit twiddling to output it. It's like not worth having a function for. Just copy pasta it.
Thanks.
Yeah.
Anyone else? Or is everyone just blown away by Stefan's talk?
All right, thank you very much. Oh, there's one more question.
Just curious if you're also publishing it somewhere.
I would like to publish it. It is, of course, it was a lot of work putting this deck together, but now that I've done this, I think we're one step closer to a publication. I also clarified a lot of things for myself about how these other RNGs work. So yeah, I think a publication would be really great. But yes, that might take me a while to get it all together. And of course, you have to run simulations and formalize proofs and stuff like that. So, all right.